So welcome back to the systems biology course on advanced modeling, and we're going to continue our analysis of the stability of the steady states of two variable systems. And what we did in the last lecture is that we introduced this phase plane, or the phase portrait, that allows you to quickly assess the dynamical behavior of two coupled differential equations. Right? So we said, okay, so we have the rate of change in the concentration of some molecule X and the rate of change in the concentration of some molecule Y. And these concentrations change because of the activity of reactions, synthesis and degradation reactions. And these rates, they sum, and eventually this gives rise, this entire sum equals these two functions. And then we said, okay, we can look at the x dt is 0 and then solve the fxy function, right? We can solve it for y. So let me note that by that inverse. And we can also look at dy dt equals 0. So that effectively means you said this is 0. And then you can solve for y. So you take this inverse of g. Okay? And this is the x null line. So on that line x doesn't change. And this is the y null line. So on that line doesn't change. So if you plot both of them, let's say you have this. So this is the x null line, the x dt is 0, and this is the y dt is 0. So this then must be the steady state. Okay? Now, on that line, the x dt is 0, so only y can change. So all the arrows must point either up or down, but they're all vertical. Along this line, y doesn't change, only x. So here all the arrows must be horizontal. That means we have four regions. This region, that region, that region, and that region. And these regions are bordered by the null lines. Now the null lines mark sign changes of the x dt or dy dt. Okay? So the null line for x marks a sign change in the x dt. So if we take a point here, okay, look at that point, and just ask what is the x dt and what is the y dt at that point. Okay, so let's say this is positive and this is negative. Yeah, that means that in this region there are no sign changes of dy dt and the x dt. So it must always be this, in this entire region. Of course, the positive values and the negative values, they can change in value, but they remain positive and negative. So now if you now cross this, you go from region 1 to region 2, the sign of the x dt will change, so you get this. X changes in sign. Now we cross the y null line, so y changes in sign. We cross the x null line again, so x changes in sign. Now we cross the y null line again and y changes in sign. So you see that these null lines, they mark regions, and in these regions the x dt and the y dt have a constant sign. But of course, so that means there is a net direction to their dynamics. But the arrows, of course, they can still point differently, because a small positive delta x or a large positive delta x or a small negative delta y or a large negative delta y leads to different arrows, even though the signs are the same. Okay? So, now using vector plot or streamline plot in Mathematica, you can add these arrows, and they point at the next moment in time. So for instance, these arrows, they could look like this, right? So that means that from a starting point, we oscillate to the steady state both for x and for y, right? Because we go like this, so they each go up and down, up and down. Okay, now if you look at the arrows close to the steady state, they may point away from it and it's unstable, and they may point towards it and then they're stable. So, but why the stability or the instability occurs close to the steady state has to do with the behavior of f and g around the steady state, right? So behavior of x and y close to xs and ys depend on fxs, yxs and gxs, yxs, right? And their values close to and ys, okay? And that's exactly what we did for the one variable system. For the one variable system, we also made this argument that the stability of this system can be analyzed by defining a new variable, which is the distance from the steady state. And if this distance to the steady state becomes smaller over time, then the system is stable. So that means we can define this. This we can substitute in on the left hand side, and x is now a constant, so any change in this sum has to be due to the variable part. And on the right hand side we substitute this again. Now we're interested in small values of delta x. So then we can approximate this. But this is 0. And this is now just a number, right? Because, and the reason, and the way to see that is the following. So if I would plot the x dt as function of x, right, I would just sketch f of x. And here there's the steady state. Because that's why the x dt is 0. So this slope is delta f, delta x, at the value of x, and that's going to be a number. Right? And that is exactly that number. So if we give that number a new name, then what we arrive at is this differential equation with this new parameter lambda. And if I take that differential equation and I solve it, then you know that it looks like this, the solution. So that must mean that if I plot x as function of time, and I have the steady state value here, and I start at steady state and then apply perturbation, that either it goes like this, so it decays, now lambda is negative, the system is stable, or it goes away and lambda is positive and it's unstable. Right? So that was the stability analysis that we did for one variable systems. Now, the same concept applies, of course, to a system of two variables. There is no reason to believe why the stability of a two-variable system cannot be assessed by a perturbation in either x or y. So if we plot that, so x-axis, y-axis, time-axis, and we say, look, this is the steady state value and that is the steady state value, this is a point. So these are all the steady state, so this just marks the steady state at different time points. And we're going to look at a particular time point. So t prime. Right? And now at that time point, t prime, we can say perturb y and ask does it go down or up. At this other time point, we could also perturb x and ask does it go down or does it go up. Or you may perturb both and ask do they go down or do they go up. Okay. Now considering the fact that we make these small perturbations such that we can again linearize the functions f and g, which we will do in a moment, I think intuitively you will immediately understand that again the solutions will be something like exponents, right? Because a solution to a linear system is always going to be an exponential solution. So this you either know from experience or linear algebra. But in the one variable case, we had one eigenvalue, but now we will have two eigenvalues because we have two decay terms. So what is going to happen, I think, so what is the expectation that I guess we all have, is that you get something like this. So you have a starting value and something with exponential decays again. Yeah. So right, so that is something like this might be the expectation, that you need the initial perturbation and then you have a decay term that's either going to be positive or negative. And these systems are coupled, so any change in y will lead also to a change in x. But we will have two decay terms, one for x, say, and one for y. Right? So we have two eigenvalues. Yeah. And the expectation is that we will have this again, this exponential decay of these perturbations. So let's now determine these eigenvalues. Now, since we're interested in the stability around the steady state, we don't need all information of f and g, because f and g has the entire information in it, at all distances from the steady state this is described. We only want to look at short distances. So again, what we're going to do, we're going to define a perturbation in x and a perturbation in y, such that the value of x is in fact given by the steady state value plus the deviation from it, and we're going to take small deviations, okay? So we need to substitute for x the value of steady state and the distance. Yeah. And these are constants. Right, so they're a number. So the change in that sum can only be due to the fact that the variable part changes. And here we apply the same variable change. And we still have to do it for y. this. So now this description holds for any deviation of delta x from the steady state, but if we only focus on small ones, then we could say, alright, we're just going to look at the local properties. The local properties of f, when you make small changes in either x or y. And the same we're going to do then for g, of course. We're also going to only be focusing on the small changes in delta x and delta y. So that means we don't need the entire functions g and f, but we only need slopes. And these slopes are evaluated close to the steady state. Okay? And we know that steady states are zero, so we end up with a description that looks like this. So we have the slopes evaluated at the steady state of interest. Okay? So these are the slopes of f with respect to x, and then you substitute the steady state values, right? So if there are multiple steady states, so if you look at the phase portrait and you know there are multiple steady states, then you have to do that for each steady state, okay? So you have 3 times this equation. For steady state 1, these values, for steady state 2, these 4 values, and for steady state 3, you have these 4 values. Okay, so now we've come closer to solving the problem. It turns out that we have to look at a matrix. We can exploit definitions of linear algebra. Where all these matrix entries are evaluated at the steady state. And now these are just numbers, right? So one example would be 0.1, and say minus 0.3, minus 0.4, minus 0.5. Okay? And this system of equations describes this type of dynamics, in the case that it's stable. But you see now that this matrix, which has a name, it's called the Jacobian matrix. This Jacobian matrix, or this sensitivity matrix around the steady state, has 4 entries, but we only need, for stability analysis, 2 eigenvalues. So we need to determine the eigenvalues from this, okay? Alright, so let's do that. Let's get these eigenvalues out. Well, understanding what eigenvalues are is not really, so let's say the linear algebra understanding of eigenvalue is not really part of this course. But I can give you a flavor of it. So, if we describe this as a vector called, let's call it z. Okay? Let's call it delta z. So that's the vector of perturbations. And the rate of change in this vector is given by the Jacobian matrix J multiplied by a vector. Okay? And considering our experience with systems that are given small perturbations, then we expect that the solution, so that delta z as function of time, right, will be a sum of exponents. One for x, delta x, and one for delta y. And the reason why we expect that is that if you give these small changes, it is the linear behavior. So the system is described by a linear set of differential equations, so with constants, right? These values don't change. And a solution to a linear system like this, okay, if you would plot that as function of time, you get these exponential-like decays if these values are small enough. So that's something you either know from linear algebra, or you've tested this by computation, or you've proven this. But we're going to look at the sum of its exponents. Okay, so that means that effectively, that if it's a sum of exponents, then a solution with one exponent, say lambda times delta z, should also be a solution. And that happens when the other exponent doesn't matter. Okay? So now we have a system where we have in fact two eigenvalues, lambda 1 and lambda 2, but the lambda 1 solution is also a solution of the system. Okay? So that means that the entire set of solutions is always the sum of these solutions. If that is true, and this has to be true when it's a sum of exponents, which is a linear algebra property, then you get something like this. Okay, then this, for the lambda value that we're looking at, we're looking for a lambda value that obeys this equation. Okay? So that lambda value is going to obey this equation. That lambda value is going to obey this equation. That means that the lambda can be deduced from this relationship. Now you may know from linear algebra that this is true if the determinant of this thing, right, is 0. Okay? So this is true if the determinant of that is 0. Okay? So that's all linear algebra that you're either familiar with or not. It doesn't, for this class, it doesn't matter so much. But it's only the equation of the eigenvalues in the end that is going to be important. So let's say this matrix, the Jacobian matrix, has these 4 entries. So what is then this equation? So j minus lambda I is going to be this. Because the I is the identity matrix. You get this? Okay. And the determinant of this guy, of this new matrix, this you calculate with your determinant rules. Take the product of the diagonal values and you subtract the product of the diagonal values, right? And that then needs to be equal to 0. So if you work this out, you get A times D minus A times lambda minus lambda times D plus lambda squared minus BC equals 0. Now if we collect all the terms that go together we get lambda squared minus a plus b times x plus ad minus bc equals 0. Okay, so apparently lambda is a solution to this equation. Okay, so the eigenvalue that we are interested in, so the eigenvalue is a solution to this equation. But it has two solutions, right? It's quadratic, so the two solutions. So two eigenvalues exist. And you also may notice something else, is that only two things matter. The sum of this, of a plus b, and this term. Now, the original matrix has all kinds of linear algebra properties, of course, but one of them is the trace of J. And that is the sum of its diagonal terms. And another one is the determinant of J, which is this. Okay. So it turns out that indeed only two properties of the Jacobian matrix determine it. It's its trace and its determinant. So let's call that d and t. So you get minus t lambda plus d equals 0. So indeed, like I said before, the stability analysis is only in terms of two eigenvalues. But we started with 4 parameters in our Jacobian matrix. But indeed, it only turns out that two properties of the Jacobian matrix determine the stability, so determine the behavior, the values of these eigenvalues, and that's the trace and the determinant of the Jacobian matrix. Okay. So now you may know that the solutions are b plus minus b, t divided t squared minus 4 times d divided by 2. Okay? Because you may remember that the general solution to a quadratic equation with coefficients a, b and c is b squared minus b plus minus b squared minus 4ac divided by 2a, right? So that is the general solution to a quadratic equation. And here we have a quadratic equation that, that lacks one coefficient. And b is negative. Okay? So this is what these are the eigenvalues of the Jacobian matrix, that guy. And so we determine the trace, and we determine the determinant, and then we can calculate what these eigenvalues are, and we get 2 of them. Okay. So let's now look at the behavior of this. So let's try to analyze this a bit further. And now we're back at the syllabus. Now we can make a plot of the determinant and the trace. And we can look at this part, so we can say, look, t squared minus 4d, when is that 0? Well, that's when d equals 1/4 t squared. Okay. So that is this.